Hello students, this is Professor Chalai, and in this video we're going to look at gas pressure relationships. By the end of this video, you should understand how a gas's pressure relates to its temperature and volume, and also understand how to use linear curves to understand proportional and inversely proportional relationships. This is sort of just a brief pre-lab lecture for your online labs on gas pressure relationships on Pivot. As always, if you have further questions, you can send me a message or come to my office hours and I can clarify anything. But let's get started with gas and gas pressure. Now, we talked about earlier in the semester that one of the properties of gases include the fact that they are compressible and do not have a fixed volume. So they have neither fixed volume nor fixed shape. And the reason for this is because gas molecules, if I can draw them, imagine the gas molecules in this little box, for example, are simply gas molecules of whatever it is, if it's, let's say, oxygen gas, just randomly moving around whatever container they're in. So these gas molecules are going to be all randomly moving in different directions. And the pressure is simply a measure of the force that these gas molecules exert when they hit the walls of the container. That's what a pressure is. So pressure is going to be the force that those molecules exist divided by the area over which sort of they hit. So you can imagine for a gas molecules, gases will be bouncing off everywhere off of these containers, and that causes the pressure that air pressure or the pressure of the gas that we're accustomed to. Now, because pressure is force over area, that means that the units for pressure would be, so unit of pressure would be the unit for force, which is in the newtons, divided by unit for SI unit for area, which is SI unit for length, meters squared. However, we would call this a Pascal to simplify it. Pascal. Now, more common than the Pascal would be the atmosphere. The unit of pressure called the atmosphere, where 1 atmosphere of pressure is the same as 101.3 kilopascal, so that's 1,000 pascals, because 1 atmosphere is about the air pressure at sea level, which is what we experience on a day-to-day basis. So this is the unit of pressure that we most often use, and that's about 760 millimeters of mercury, which was used in old-timey thermometers, which is about 760 torrs. Millimeters of mercury and torrs are the same thing. So those are some units of pressure that I thought I'd mention to you. But they come from the force that the molecule exert as they hit the walls of the container. Now, let's just briefly look at how two things might influence the pressure. The first is temperature. Now, when we think of temperature for molecules, let's just imagine that what the temperature does is make molecules move faster. So if you're thinking the temperature of a solid, it's just going to make the molecules vibrate faster. If it's the temperature of a gas, then it just means that the gas molecules are zipping around faster in the room. So if that's the case, then these molecules will be hitting the walls of the container with even higher velocity. So that means that if the temperature goes up, right, the pressure should also go up because the force that the molecules are hitting the walls of the container are going to be higher. So that's for temperature. Let's examine the same phenomenon now with volume, right? If we have a volume of gas, they're zipping around, hitting the walls of the container, as we've discussed. What happens if you make that volume, let's say, smaller? Now, all of those same gas molecules are in a tighter space. They're still moving around with the same speed because the temperature is the same, but they're in a tighter space, which means that the time it takes for them to hit this container wall and then go back and hit this container wall are going to be, the time's going to be shorter, which means they hit the walls more often, which means that the pressure goes up because they're hitting the walls more often. So in this example, as volume goes down, pressure goes up. So this is for volume. So those are the two ways that volume and temperature can affect the pressure. And our lab is going to explore those concepts further. The second thing that I wanted to touch on in this video is understanding how we can explore these relationships using curves, linear curves. And so to do that, let's look at the equation of a curve, a straight line, again in more detail. So the equation of a straight line, as you know, is y is equal to m times x plus b. Now, to make this discussion a little bit simpler, let's ignore b. And let's just look at this equation, y is equal to m times x. So we have our graph, right, with our data, and this is our line y is equal to m times x. M would be the slope. It could be a positive slope or negative slope. Let's just look at a positive slope for now. What this means is if we have a positive slope, as y goes up, x also goes up. This sets up what we call a direct relationship. That means that y is proportional to x. Or as y goes up, x goes up. If y goes down, x goes down. Let's look at another relationship. Let's look at the curve y is equal to m times 1 over x. X is now in the denominator, so if y goes up, x needs to go down, and vice versa. This is what we call an inverse relationship. So these are the two types of relationship we're going to explore in this week's lab. And so just to keep this in mind, if y is proportional to x, you have a direct relationship. And if you have an inverse relationship, it means that y is proportional to 1 over x. Or as y goes up, x goes down, and vice versa. So if you plot a curve of y against 1 over x, so in the first case, this is a curve of y against x. In the second case, if you plot a curve of y against 1 over x, you will see a straight line for an inverse relationships. So those are two types of relationship we'll be exploring in this class as we explore how temperature and pressure are related and volume and pressure are related. As always, if you have questions, please send me a message or come to my office hours and we can discuss them further. But these should be the beginning steps of what you need to know to do this week's lab. I'll see you in class next time.